The first presenter is already here, Daniela Maria Tizea. We're going to give a presentation about record-to-record travel algorithm for biomolecules structure prediction. So you can start the presentation. Daniela, consider that you have 10 minutes plus 5 minutes for questions. So try to be on time. You can start sharing your screen.
Yeah, now I will do a share screen. First of all, thank you for the presentation. Nice to meet you.
Nice to meet you.
The title of the paper that I will present today is named Record-to-Record Travel Algorithm for Biomolecule Structure Prediction. We are two PhD students from Babeș-Bolyai University, Faculty of Mathematics and Computer Science, from Cluj-Napoca, Romania, and the country of Dracula. Maybe most of you heard about it. I will try to be short, but it's a little long, the presentation, but I will do my best. The schedule for is about protein structure prediction on the hydrophobic polar model with a record-to-record travel algorithm. We'll introduce you in proteins because proteins are important compound of life matter, which they found in all living things. They are macromolecules built of amino acids and because a giant molecule, they have 4 structural levels: primary, secondary, tertiary, quaternary structure. The primary structure is synonym with amino acid sequence. The tertiary structure is synonym with conformation. Now, about protein folding. Is the process by which the protein throughput the primary to the tertiary structure. This process is very important because the protein has a biological function only in the tertiary and quaternary structure. Protein structure prediction supposes the prediction of tertiary structure from the primary structure. The protein has only one primary structure. Instead, it has myriads of possible conformations. Only one conformation, called native conformation, has a suitable biological function and has a good conformation. Because the conformational space is immense, over time, several models have been introduced in order to simplify the problem. I will go further with hydrophobic polar model because it's one of the simplest that we choose, proposed by Deal in the 80s. It has the following simplification. The 20 types of amino acids are restricted at 2 types, hydrophobe and polar. Amino acids are placed on the nodes of the lattice. In this paper, we have working on 2-dimensional square lattice. In the model, it is introduced an arbitrary energy, the same of the free energy from thermodynamics. Here you can see the lattice. Now, we worked together at the same PhD thesis, yeah, and is an interdisciplinary area, multiple area from biological, computational, chemistry, computational, mathematical, and now I will introduce you in the mathematical area. A mathematical model for protein structure prediction was used with a Now, first formula represents two-dimensional lattice where the scalar b1 and b2 are integer numbers, and the vectors v1 and v2 are the basic for R square. The v1 and v2 meet the condition. v1 is perpendicular to v2, and the norm of v1 is equal with the norm of v2. Thereby, lattice is a square whose sides have length 1, and amino acid spatial position is restricted to precise points in space, because the main role of the lattice is to divide the continuous Euclidean space in a discrete space. Sorry. Yeah, it's mentioned here. I will go further to optimize this model for protein structure prediction problem on 2D lattice. We have a minimized problem based on the minimum energy principle with the following restriction. Equation 2 is full energy of string C, that means protein conformation. Equation 3 fix the first amino acid on the HP string, the center in the center of the lattice. Equation 4 fix the second amino acid and n plus 1 position. So we consider n vertical and n plus 1 horizontal. On the lattice right direction, by constraint reduce the combinatorial space for 4 times. Next, equation 5, 6, 7 constrain that the walk in the grid occupies exactly n nodes. Each lattice nodes cannot contain more than 1 amino acid, and 2 sequence neighbor amino acids occupy the adjacent node in the lattice. So this 2D vector coordinates of the lattice, and kappa is the kappa form amino acid in the HP sequence. So 0 means it's not here. 1 means that there is only 1 amino acid at position AG, and 0 means that at position AG there is no amino acids. Okay, now like I said, the other discipline that we use is computer science. So to move into the area of computer science, we use to solve the protein structure prediction problem with record-to-record algorithm. Record RRT is a variant of the Great Deluge algorithm, a local search method, and is created by Duke in 1993. And is being distinguished by the author by different circumstances. RRT water level increase is given by the quality of the best solution found until the iteration. And we use a record parameter, which will be updated only if the quality of the best solution is greater than its value. So record, you can see here, is the level water that rising. So gets a negative value. Deviation is half of record and is the height of the man and is set to a negative value close to 0. So the algorithm described here is very shortly first set the deviation above the water, and for each iteration a perturbation is applied to the old solution. If energy is new solution, that means that is better than old one. Different from the other author from Duke, here the solution don't pass because it's submerged. But RRT algorithm permitted the water increase and upper than gneiss of the human. Okay, yeah, I still have some slides if you let me. So the description include 3-stage representation of configuration. Here I want to mention some data structure that we use: HP string, the input parameter for RRT, and the right, up, left, and down string. That is the output one. Both have the same length, and the chromosome class, which encapsulate the two types of string. Next one, another stage can be evaluation of the conformation. The algorithm counts the number of contacts, each topological neighbors, and we have two mutation, a way to see the chaotic behavior of the energy function on the hydrophobic polar model. Weak conformation or chromosome means an energy from -4, and an optimum conformation is an energy with -9. Yeah, I talk about the algorithm. Some sequence that results after the benchmark. Here I want to mention the comparison with other 4 best optimal solution obtaining by other authors, the genetic algorithm based on optimal secondary structure, evolutionary Monte Carlo, and genetic algorithm hybridized with a great deluge algorithm. And for relative sequence, if n is smaller than 50, smaller or equal, RRT produce the best results. That means that find the conformation with the minimum free energy node. For if n is greater than 50, not reach the optimal solution. And here we can see the lattice represented, and we account for this energy to be obtained -9. Only the pair HP, only this we compute. Okay, some conclusion or future words better. We want to improving our algorithm, also in convention with a genetic algorithm, and extend the lattice model.
Okay, thank you very much. Thank you for your presentation, and Are there any questions for this presentation? About this presentation? Anyone want to ask something about this? Okay. I have just a very short question because I didn't know about this record-to-record approach. But is it a probabilistic measuristic? So because you mentioned that you had to repeat for 50 times the optimization. So I suppose that table reported the average of those 50 runs, no? Can you confirm this?
Yeah, of course. And yeah, it's methodistic and it's combinatorial. And yeah, I want to mention the advantage that why is you can use it because it's time efficient, requires more computational resource, has only 2 tuning parameters, deviation and the maximum iteration. Easy to implement.
Okay. Yeah, no, I see, but you didn't show the computing times, so we couldn't appreciate that.
Yeah, sorry.
You only compared the accuracy of the result, the average accuracy, but
Yeah.
okay, thank you very much. Thank you very much. I think we can move to the next presenter.
Thank you also.
Thank you. The next presenter, Jerzy Resondek, who will present a paper entitled Another Dubious Way to Compute the Exponential of a Matrix.
Yes.
So you can now start your presentation.
Okay, so let me start sharing the screen, but I guess that my previous the previous presenter, yes, now I should be able.
Try to.
The previous presenter, I'm clicking on sharing the screen and nothing appears, unfortunately.
So you are not able to share the screen, you mean?
Well, let me go once more into the. Let me once more run this. Please wait a moment.
I've been closed my presentation. My share screen.
Try now to share the screen. The third button. Okay.
Okay, perfect.
I don't hear the presenter.
Me too.
Please enable the microphone.
Now you should can hear me, yeah?
No,
can you hear me now?
Yeah.
Now, yes.
Yes, okay, so let me once more share the screen.
Okay.
The title, so let me restart. The title of my presentation was another double ways to compute the exponential of matrix. A few years ago, appeared a famous paper on how to, in the 19th way, how to calculate an exponent of a general form matrix, a generic matrix. My presentation was about how to find an exponent of a particular class of matrices. It means the so-called companion matrices, by some people calling it companion Frobenius matrices. The objective of this presentation is to show how to find the exponent of a companion matrix. By this particular example of special matrix, it means companion matrix, we show how to improve the time complexity of proper algorithms yielding from its special structure. So in other words, I implemented special structure matrices to find exponent of certain matrix. And the main tool, as in my method, is a so-called confluent van der Monde matrices. The van der Monde matrices appears in classical interpolation, but we have some generalization of that. I concentrated on the generalization of confluent van der Monde matrices, which have the following broad route of application: linear ordinary differential equation. The general canonical form of the matrix, it will be in a moment in the presentation. Control problems, investigating so-called controllability of higher order systems with multiple characteristics, multiple zeros, leads to problem of inverting the confluent van der Monde matrix. Interpolation, another application of confluent van der Monde matrices is interpolation. At the academic course, during our study, each of us have met the classical interpolation, but besides classical interpolation, we have with single nodes, we also have a special generalized interpolation, a special generalized Hermite interpolation, which allows multiple interpolation nodes. Such an augmented interpolation enables to control the slope and the convexity of the interpolation curve in each point. So we gain control over sloping and convexity. Another application is information codings. They are applied in Hermitian code. We define it as a block matrix. How we define it? For ordinary van der Monde matrices, the characteristic polynomial have single nodes. Here we allowed the nodes to be multiplied. And classical van der Monde matrices have only blocks like this, but we have also some confluent blocks. For example, for the polynomial with two zeros, -2 and +3, you have the following matrix of two blocks. The confluent van der Monde matrix is just the main tool in my article. The proposed method basis on the reale that the Jordan canonical form similarity matrix of companion matrix is just a confluent van der Monde matrix. It may sound a little sophisticated, but it will become clear by the example during the presentation. So the companion matrix is defined by the once again by the characteristic polynomial, and the matrix form is as follows. We have ones on the not mine diagonal, and coefficients, subsequent coefficient of the characteristic polynomials at the bottom, and all the remaining entries are 0. To calculate the coefficient A0 to n minus 1, we have at first to rewrite the characteristic polynomial in called flattened form. It means that we are assigning to each multiply 0, we are applying a series of the zeros which are equal to each other. We are grouping it in the following R groups, and after expansion the polynomial paired S, and we sort it with respect to decreasing powers of the S variable, we just obtain such characteristic polynomials where small w's are so-called elementary symmetric function, which are defined by the following formula below. Symmetric function is it means that after any permutation of its independent variables, we obtain just the same function more. And these are elementary symmetric function, and the problem transfers here is to calculate the elementary symmetric function. The elementary symmetric function we have in the literature algorithms which can do it in quadratic or even faster way. Companion, but now let's return to our companion matrix. Companion matrix can be written in the so-called Jordan canonical form. So the companion matrix is the similarity matrix multiplied by Jordan block, elementary block matrix, and the inverse of that. And the soul of the proposed method is that we just the similarity matrix for the companion matrix is just the confluent van der Monde matrix. So when we possess an efficient algorithm to invert it, we can also to find the exponent. It's easy to computer because general function of a matrix in is when we apply function to the matrix in Jordan after Jordan decomposition, we apply the function to C, and we apply the function to the internal Jordan block, which is relatively easy to calculate. So when we are finding exponent of a companion matrix, the problem shifts. We can call it the problem shifts just to the finding the exponent of a Jordan canonical form. Finding the exponent of Jordan canonical form isn't hard because we have already formula, because the elementary Jordan block have the following form of two diagonal of only main diagonal and ones just above the main diagonal, and arbitrary function is how to apply to it is now from the literature. Function applied to this one matrix have the following form as just at the right. So when we transform the problem of finding exponent of companion matrix to finding exponent of a Jordan block and inverting the van der Monde matrices generalized. In other words, we write it in the following. X of t is equal exponent for the differential equation exponent of at, and the exponent is just equal to similarity matrix T exponent and inversion. And the similarity matrix T, in other words, we can call it Jordan canonical matrix T of Frobenius matrix A. Frobenius is another word for companion. Is ordinary van der Monde matrix in the case of single roots of characteristic polynomial, and confluent van der Monde in the case of multiple roots of the characteristic polynomial. To sum up, finding the exponent of accompanying methods requires the following step: building the confluent van der Monde matrix and Jordan block matrix which we can perform in quadratic time. Next, we must to invert the confluent van der Waals matrix. It's just quadratic, also due to my algorithm from another article. Next, we should calculate the exponent of the Jordan bar in quadratic time. We should apply the formula. Unfortunately, here is the matrix multiplication, and we can find it in cubic time. And so this is the slowest step, and calculate the elementary symmetric function, quadratic step. So we have found the exponent in a cubic time in general, but in an accurate way because all the applied algorithms have numerical stability on a high level. Next, the literature on this is just Miller's reference paper Moller van Loa 19W way to compute exponential of a matrix. Numerical analysis is a classical book on numerical methods. Next is how to invert that's not from me, the barking of a dog. I don't possess any dog. I see how to invert the van der Waals matrix. We have two works to invert classical van der Waals matrices, and we have also works on inverting confluent van der Waals matrix by another author. How to calculate the elementary symmetric function can be found just in this one position. I do not possess a dog. Vidysagar have proposed another model of calculating exponent, but for a general matrix. We have also works which pertain to exponent of a confluent van der Waals matrices. This one position calculates exponent just of the confluent van der Waals matrix itself. But here it's interesting, but in this presentation, the confluent van der Waals matrix was only a tool how to find the exponent of of a companion matrix. Another famous author is Kingham.
I think you have to conclude now.
Yes, I am going to conclusion. So the conclusion, orally, the conclusion is of this way that I have proposed efficient and elegant method to find the exponent of a particular class of special matrices. It means companion matrices. In other words, Frobenius matrix. Thanks for your attention. I'm trying to launch the camera, but unfortunately, I don't know why it doesn't work.
It happens. Okay, thank you very much for your presentation, and I would like to ask for questions. Are there questions? Or
yes, I wait for your question.
Let's check if we have questions. Okay, apparently no. So I would like to thank you again for presenting your work at the conference, and I would also ask to the attendant if there is one of the authors of the third paper, application of mathematical models to estimate and so on. Is there anyone for this paper? Because apparently I cannot recognize any author among the people connected in this room. So is there anyone for the last paper? The last paper?
Yes. Yes. My name is Luis Martins. I will be presenting the fourth paper.
So you are Luis Martin, okay.
Yeah.
Because I couldn't see your name before. I don't know why. Okay, so we have to skip, necessarily to skip the third paper. We can start with the last paper. It will be presented by Luis Martin. The title is Building Energy Performance Comparison between Energy Plus and other certified tools. So you actually, I think you have more than 15 minutes. More than 15 minutes. You can start.
Okay. I think I shared my screen.
Yes.
Yes.
Yes. Thank you, Mr. Chairman. So the title of my presentation. So I'm sharing the screen. Is that okay?
Yes, yeah, it's okay.
Okay. Building energy performance, comparison between Energy Plus and other certified tools. The contents of my presentation is basically the background and objective of this study. Then I will describe the case study, followed by the methodologies used in 3 different types of simulations, some results and discussion, and final remarks on future work. The building sector is the main energy consumer in the European Union. It represents about 40% of the final energy demands and 36% of CO2 emissions. In Portugal, where I come from, it's a little bit less, so about 30% for final energy consumption. It is well known that it's possible to reduce by 50% by using energy efficient measures. Therefore, the building sector is of capital importance for reducing energy consumption in the European Union, minimizing the negative impacts of global warming, and achieve the European Union goals. Those goals for the energy building sector is, as we are now in 2021, all new buildings have to be nearly zero energy buildings. So the energy balance of a new building has to be close to zero. And by 2050, the building sector should be carbon free, totally carbon free, which is a very, very difficult goal to achieve, I think. So most thermal modeling of buildings for energy consumption in Portugal and the European Union is made in 3 ways, depending on the type of building and increasing complexity. So the general objective of this work was to study the energy performance of a simple residential or service building. So we used a simple building for both purposes in Portugal, in the north of Portugal. The specific objectives were the assessment of one of the most used building energy simulations, which is Energy Plus, which is very famous, and other spreadsheets available on the market for the European regulations that fulfill the European Energy Performance of Buildings directives. So we want to determine the thermal loads and annual energy consumption, and verify the veracity of the results comparing the different tools. The case study was a very simple building, considered as a residential or a small service, only with 60 square meters, so a single zone, 10 by 6 and 3 meters high. And the energy simulation tools were 3, as I told. The first one is a very simple one. It's applied to residential buildings. So it's a spreadsheet for residential buildings. In Portuguese, is called this regulation is called the REH, for Energy Regulation for Home Buildings, and it applies a seasonal method. The second simulation tool is a spreadsheet for commercial and services and buildings, but this is already a simplified dynamic simulation. The Portuguese number for the regulation is RECS. CS stands for commercial and service buildings. And finally, the Energy Plus. The Energy Plus is a very famous code used worldwide for detailed dynamic simulation of thermal simulation of buildings. Any simulation of a building goes through an energy balance for winter and usually for summer, where in winter, usually you have to, the overall balance of the building is more losses than gains. So we have to provide heating system to maintain a temperature which is usually 18 degrees Celsius or 20 degrees Celsius, depending on the building and the country. And in summer, usually you have to take out, so you have to cool the building, so to maintain it at comfort stage, which is usually considered 25 degrees Celsius and relative humidity of 50%. In this case, for all three tools, we use the same building and the same materials and construction. So,
Luis, excuse me, can I interrupt you? But I'm still seeing the title of the presentation. So you are not.
Oh, sorry.
For some reason.
Something went wrong then. I will go back. Because I was trying to share the window, but I'll share.
Also consider that now there is also the presenter of the previous presentation. So we are actually very late. So try to be really synthetic.
So am I sharing the screen now?
The screen, we see a kind of...
yeah, it's a big mess. But let me try to go back to my presentation.
Try to put it in full screen mode. Maybe you should put it...
Yeah. Is it okay now?
Okay.
Now, apparently, yes. Apparently.
Okay, so I was talking about the energy balance in winter and summer. So the conditions and now the materials and construction. We analyzed two cases. One is a non-insulated building where the global transfer coefficients for the walls was 2 watts per square meter in Kelvin, and with the insulation, the reduction is by more than 5. So this is just an example of the walls. So of course it's very important to insulate a building, and we change the transmission factor by a large factor. In the case of this first method, so seasonal method, the climate data is very simple. It's all here, and is based on the main important characteristic of the climate is the degrees days of that region, that area where the building is, which is in this case is 1629 degrees days. And this is the basics for the calculation of the thermal loads, so the thermal losses in winter. Only the radiation in the south facade is needed for the total season, and for the summer it's even lower, only the period and the average temperature. But for the solar radiation, some more numbers are needed, but basically the radiation in the different facades of the building are needed. But this is all we need for the first method. In the case of the two other dynamic simulations, so the RECS, which is a simplified one, and the Energy Plus, the climate data is the same. It's a typical meteorological year, which is generated by a software in the case of Portugal for the different areas. And so it's hourly data. You get a file with temperatures, air wind velocity, humidity, radiation in different surfaces every hour of the year. It's a typical year. And in the case of the Energy Plus, we use the 3D software to design the building envelopes, SketchUp Pro, together with the Open Studio to define the physical and thermal characteristics. These softwares were very useful and user-friendly to connect with the Energy Plus code, which fulfills the ASHRAE 140 standard, usually everywhere in the world. Again, for these two types of systems, you can define the operation profiles. In this case, the schedules were defined for the whole year from 6 a.m. to 8 p.m. And it include profiles for occupation, electrical equipment, and lighting. In the case of this first system, the seasonal method, the calculations are very easy and made only for the whole season, winter and summer. And so in winter, you just calculate all the losses through the walls, through the ventilation, air ventilation, and also the gains, the heat gains by solar radiation and by internal radiation. And in the summer, we have the gross gains that are affected by a function, y minus a function of efficiency of the gains. So all the gains that the building gets in the winter, some of them are not useful. and it depends on the inertia of the building. So the calculation of these gains in winter and in summer depends on a function which involves the thermal inertia of the building. In the case of the simplified dynamic simulation for the commercial and service buildings, the heating and cooling demand is done through an energy balance on an hourly basis, as I said, according to the European norm, which is used in Europe. And the heating and cooling needs are calculated using a Crank-Nicolson iterative method. There is an analogy with the 5 resistance and 1 capacitor electric circuit. The inertia of each envelope component, like a wall, is just simulated by a single node with a single mass, which is the capacitor. And this is a different approach and simplified approach when compared with the Energy Plus. The Energy Plus uses semi-implicit Crank-Nicolson and finite difference methods, which is much more accurate, or it should be more accurate in terms of the dynamics of the inertia of the envelope walls of the building. And that's, again, the radiation is also treated in a more accurate way. Some results in this figure, I can show the results for a critical day in summer on the left, and a critical day, sorry, on winter day on the left, and summer on the right. So heating demand and cooling demand. This is one day in summer, one day in winter, one day in summer, and the final results are below. So the heating demand for the Energy Plus, REX, and REA, the basic steady state mode, which only gives results for the full season. And you can see that in the winter, the conditions, the results are quite good for the 3 softwares, even the REH, which is not dynamic, but the cooling demands are different. And the REH is not accurate at all for calculating the energy demands in summer. This was the building without insulation. Of course, with insulation, the heating load goes down a lot, as you can see. So the peak was before something like 9 kilowatts, and now it's less than half. And again, the heating demand is reduced, but because there was no shading on the windows, the cooling demand increased in the case of Energy Plus and the RECS, which was expected, because when you insulate a building, you have to shade the windows facing south in particular. Otherwise, you will have overheating, and you get better results in winter and less gains of heat in summer through the walls, but then you get lots of sun radiation, and it doesn't compensate for the insulation. The final remarks are that concerning the thermal loads, the simulation of the building without insulation using Energy Plus showed heating and cooling results similar to RECS, 10% lower and 6% higher. But REA, the discrepancies are much more significant, especially in summer, so you cannot evaluate. And REA is just a system of comparing different buildings, but not for really evaluating the consumption, energy consumption of the buildings. So, which means, but anyway, in winter it gives quite good results, but in summer the results are really poor. Of course, even the differences between RECS and Energy Plus were expected, because the RECS is a much simpler algorithm as compared with Energy Plus. The results show that the insulation reduces the heating demand, but on another side affects the cooling demand when compared to the building without insulation. The high cooling demand is due to large size of the windows and non-existence of shading devices. So for future work, we did some of that already. We will test windows with different shading elements, influence of thermal inertia, and define a more realistic building. And we will try to do some validation with an experimental instrumented test building. Thank you.
Okay, thank you very much. Thank you very much. Is there any question? Okay, actually, we run out of time because there is another presentation and we are quite late. But just a very quick question. But you compared essentially models, different models. So I was actually wondering, but Energy Plus, which is quite a famous application, has been compared with the reality, for example, real buildings, and did you perform any check?
No, not yet. We didn't. That's what we intend to do with a simple building, because it's when you have a very complex building, it's very difficult to validate because of the different schedules. In a complex building, the schedules change a lot. So if you don't put the right schedules, you get differences, and it's not because of the software, it's because of the schedule. So in order to validate, you need to start with or we need to use it in a quite simple building, but you have to instrumentate it. So it's quite expensive. It's not easy to do it.
It's quite a difficult thing, actually.
Yes.
I imagine. Okay, thank you very much again for your nice presentation. Now we have the last presenter, Flavio Guterres. I suspect I didn't pronounce it very well, the surname. Okay, the title of the presentation is Application of Mathematical Models to Estimate the Water Level Stability in Two-Tank System in Series with the Service Demand Variations. So, Fabio, you can start your presentation now. You can share your screen. Are you still here? Can you start your presentation? But Natale, can you hear me?
Yes.
Okay, so probably we have some maybe the speaker has some connection problem, because a few minutes ago he was writing, complaining about but apparently maybe in the chat. I will send you in a private message, maybe.
I don't know.
Apparently he is here, but
He wrote
he cannot essentially. The problem is that he cannot hear me, but if he cannot hear me, he cannot hear anyone. So that's quite strange and weird. I am asking him to start the presentation, but
enable the microphone. Yes. If you have a problem, try click on 3 dots and set your microphone.
I'm giving him some suggestions, some advices. Maybe because sometimes the microphone is okay. This is a good idea. So at least we discovered why it didn't reply.
Okay. Try to change the device. If you have a smartphone, try to smartphone to present.
No, the only way is to write messages, text messages. So I'm asking him if he has another device available, but
Okay.
Is on.
otherwise we can try to maybe there is another slot in another session. I don't know, because now it's quite difficult. I suspect it's. In practice, now it's. I think it's too late now to start another presentation. What do you think, Natale?
Aspettiamo un attimo, vediamo cosa possiamo fare, altrimenti segnalo allo staff e recupererà un'altra volta.
Yeah, this is. Okay, I think we can wait for just another minute. Just a minute. And the best option is actually to check for another slot in another session. Yes. Maybe even in the next session. I don't know how many papers. Maybe there is room for. La cosa strana è che lui non ci ha mai non ci ha sentiti per tutta la sessione.
Sì, infatti.
Cioè, non si è posto il problema.
Sì, non capisco come sia possibile.
No, dico, okay, I think the best option is to conclude this session.
Yes.
Because in any case, we don't have enough time for another presentation, given that in a few minutes we have to start another session in the same room. So I think it's much better to conclude here the session, and then the presenter will contact the organizers for finding a solution, a good solution. Okay, thank you very much to all the presenters, to the attendants, and we will meet again in a few minutes in this room for another session of the general track of this conference. Goodbye. Okay, welcome, good afternoon, welcome to the session, another session of the main track of the International Conference on Computational Science and Applications. We have 4 papers. I would like to ask, first of all, how many presenters are already connected with us in the room. I can see the first presenter.
Yes, hello, I'm here.
The first presenter. Is there anyone for this? Please?
Yeah, I'm gonna give the second and the third presentation.
Ah, fantastic. Okay. Is there anyone for the last presentation? Let's see. Miroslav Petrov and Todorov? Apparently not. So at the moment we have 3 presentations. Okay. It's better to start with the first presentation. The presenter is Kirill Kadishin. No.
Kirill Gadilshin.
Sorry for the pronunciation
Okay.
of the name. The name of the title of the paper is Reconstruction of the Near Surface Model in Complex Seismological Conditions of Eastern Siberia, utilizing full waveform inversion with varying topography. You can start your presentation. Try to stay within the assigned time. It's 10 minutes plus 5 minutes for queries and answers.
So can you hear me and can you see my presentation?
Yes, I can see the presentation.
Okay, let me start. Well, my name is Kirill Gadilshin, and I'm senior researcher at Institute of Petroleum Geology and Geophysics, and this is our collaborative work between our institute and a company, namely RN Exploration. The title of my presentation is Reconstruction of the Near Surface Model in Complex Meteorological Conditions of Eastern Siberia, utilizing full waveform inversion with varying topography. Well, this is the outline of my presentation. I start from the motivation, continue with near surface reconstruction using the data with free surface related multiples, and finalize my presentation with deep touch horizons reconstruction and high frequency FWA. Seismic survey in the vast territory of Eastern Siberia are carried out in seismic and geological conditions of varying complexity. Obtaining a high-quality dynamic seismic image of the area of work is a priority task in the conditions of contrasting heterogeneities of the near surface. For this, it's necessary to restore an effective depth velocity model that provides compensation for velocity anomalies and calculates static corrections. We used a realistic p-velocity profile in our numerical experiments, which is presented on this slide. For full waveform inversion, we choose a part of the model designated by a red rectangle. The horizontal size of the model is 24 kilometers, while the depths reach 2.8 kilometers in depth. The main difficulty in reconstructing the near surface are caused by the presence of trap intrusions. The velocity propagations of p-waves in which reach 6,500 meters per second. Thus, the velocity difference when crossing the intrusion boundary reach 4,500 meters per second, which significantly complicates the use of standard approach to recover the depth velocity model. The presence of varying topography also complicates the velocity model building. It's necessary to perform full waveform modeling on a fine mesh to mitigate numerical dispersion caused by staircase topography approximation on a rectangular grid. An example of a synthetic seismogram calculated in acoustic mode, taking into account the multiples caused by the presence of a free surface, is shown here. Well, the acquisition contains 240 seismic sources. It's a vertical point source type with a step of 100 meters. The receiver step is 25 meters, and the maximum source receiver offset is about 5,000 meters. The inverse dynamical problem is considered as a solution of nonlinear operator equation, where F is a nonlinear forward map, which maps model space M into data space D. To simplify mathematical calculations, we deal with the scalar wave equation in the time-frequency domain. That is the Helmholtz equation. The common full waveform inversion formulation is to find the minimum point of the misfit functional, characterizing the mean square deviation of the registered data from the calculated for the current speed model. As an initial guess for FWI, we use a vertically inhomogeneous model, which was built using the well information by Gaussian smoothing and adding a free surface topography. Thus, the depth velocity model contains no information about the presence of high velocity near surface anomalies. And as I said before, the contrast is about 4,500 meters, which is very huge for any standard depth velocity building procedure. So this is a quite challenging model. Taking the surface-related multiples into account during the inversion, reduce the resolution and the information content of the FWI results. However, it increases their stability in the presence of uncorrelated noise. Therefore, at the third stage of FWI, we use the entire wave field, including the surface-related multiples. The result of near-surface inversion are shown here. The inversion was performed in the temporal frequencies range from 3 to 10 Hz, and the target area was limited up to the depth of 1 kilometer. As one can see, with such an acquisition system and frequency range of the source signal, the presence of low frequencies, we successfully identify high-speed anomalies. However, areas directly under the traps were restored with significant distortion. Therefore, in subsequent stage of FWI, to improve the restored model's quality, it's proposed to use the data without surface-related multiples. For reconstruction of the deep target horizons, to improve the restored model quality, it's proposed to use the data without multiples associated with the presence of a free surface. While performing FWI in the time-frequency domain, it's common practice to use overlapping frequency groups. In our case, after the near-surface reconstruction in the frequency range from 3 to 10 Hz with surface-related multiples, we use the following set of frequency groups to be used in FWI without surface-related multiples. Namely, from 3 to 10 Hz, from 8 to 20 Hz, from 15 to 30, from 20 to 40, and finally from 35 to 70 Hz. The starting model, the starting velocity model for each frequency group in the velocities is the velocities from the previous FWI run. For example, the output of FWI for a frequency range from 3 to 10 Hz is an input for 8 to 20 Hz FWI, and so on. Here represents the reconstruction within the same frequency group, but without using of surface-related multiples. And now our area of interest is the whole model. So one may see that we started to reconstruct the area beneath the high-velocity anomalies. And these results are still not sufficient, so they starting to increase the frequency range for the inversion and go theta. Here's the results for frequency range from 8 to 20 years. So as we increase the frequency contents on the data, we include more details into the inversion results. Here's the comparison results from stage 1, stage 2, and stage 3 of FWA. As we go further, we're starting to converge to the true velocity distribution. So next is the stage 4. And here is the stage 5 from 20 to 40 years. Now this model is very close to the true one, and the final experiment is the high frequency of FWA. So we limit our upper frequency is 70 Hz. So next is the quality control of the reconstructive model. So we fix the source location at the top of the velocity intrusion indicated by the red star, and we use three vertical profiles indicated by red lines. And here's the vertical velocity profiles. Here's the black plot is a true velocity distribution. The green plot is a starting model, and the blue plot is a near surface FWA, results of near surface FWA, and the red plot is the final high frequency FWA model. And one may observe almost perfect reconstruction of the inverted high frequency FWA model. And at the end, let me demonstrate the data feeding. So FWA is a data feeding procedure. So the idea is to find the velocity model which explain the observed data. So here's the observed data for the shot indicated on this slide, shot position, and here's the starting model, which is quite different from the observed. Here's the model of the near surface FWA and the final FWA model. So the observed data and the final high frequency FWA model data. One may observe almost perfect reconstruction. And here's the data residuals in starting model. So in ideal case, we should observe the zero difference. In real situation, we will never reach the zero. Here's the near surface of FWA. We explain some part of the data, and the final data residuals in the final model explain most part of the data. So let me conclude. So we propose the FWA workflow for accurate near surface update and consequent reconstruction of deep touched horizons. The high frequency FWA results up to the 70 Hz demonstrate high quality depth velocity model reconstruction. The final FWA model explained most part of the seismic data, even in the areas shielded by the high velocity anomalies. Our future investigations are focusing on the application of the proposed FWA workflow to the real land data from Eastern Siberia. Thank you for your attention.
Thank you very much for your presentation, and now I would like to ask if there are questions. Any question concerning this presentation? Okay. So thank you again. Thank you again. We can move to the second paper of this session. The second paper, if I well understood, will be presented by Vadim Lisita, as well as the third paper. And the paper is the presentation concerns paper entitled "The Numerical Solution of Bio Equations in Quasi-Static State." So, Vadim, you can start your presentation now.
Okay, can you see it?
We can see the slides, the first slide, yes.
Great. So good morning, everybody, or good afternoon. It depends on where you are. And so my talk is about numerical solution of bioequation quasi-static state. And I'll start it with explanation what is quasi-static state and why we need it. And the idea here is that if we so the typical problem of digital rock physics is that we need to upscale the properties of the rock starting from I don't know, pore scale representation of the rock, go into the reservoir scale. And then one of the most important feature of the rock is the elastic properties and elastic impedances of the formation, to be able to apply such an advanced techniques as fully formed inversion as in the presentation being given just before mine. So the idea, and there are a lot of ways to do it, and starting from ultrasonic wave propagation and measuring the velocity in the core sample. But the problem here is that if we've got inhomogeneous media, and we need to be able, and the sample is quite small, and we need to be able to predict the properties of the media when the long waves propagate through it. We cannot do like just wave propagation through small sample. We need to do something else, and this procedure is typically called forced oscillations, which can be represented as a loading of the sample with very low frequency resonating forces. That's the main idea on how it works in lab and how it works in numerical simulation. So why we are so abused about bioequations? Because if we go from just direct representation of the core sample with pore and matrix presented directly, we can upscale elastic properties up to the core scale, where we can use biopore elastic medium representation. However, it's not appropriate representation for seismic modeling or seismic inversion, and we need to proceed further. So in this presentation, we start with bioequations, biopore elastic media representation, and we assume that this media is inhomogeneous. It's filled with the layers or cracks or whatsoever, which are porous material itself. And this inhomogeneous porous material has to be upscaled to be so that seismic processing guys could be able to interpret the seismic observation and to link it to our pore elastic models. That's pretty much the idea. So we need to go from bio model to viscoelastic model, where we can represent just wave propagation through quite a simple viscoelastic model. And that's what the talk is about, actually. So what are bioequation and quasi-static state? The quasi-static state assumes that we've got like not wave propagating regime, but diffuse regime. And the equations are parabolic in their nature, and it is easy to solve them in frequency domain rather than in time domain. And that's how we finish up with quite a nice elliptic equation with like complex formally it can be considered as an elliptic equation with complex frequency shifted operator added in here. So this parabolic equation can be solved numerically, of course, but what we need to do to know about it is how to implement it and how to upscale it to obtain the viscoelastic model. So first step, of course, is and first question here is how to solve this system of equations. And the standard approach in seismic exploration in geophysics is to use finite differences, because the model is extremely complex, and it's almost impossible to use advanced techniques like finite elements, because we would never get a good approximation of the model better than what we've got from grid-based approaches on using regular grids. So we finish up with finite differences, and these are staggered grid finite differences, where the different components of the displacement vectors are defined at different spatial locations. So the sketch of the model and the sketch of the scheme, actually the stencil of the scheme, are presented over here. And to apply the quasi-static loading, we need to perform 3 types of experiments with 3 different loadings, and they are like represented here using different colors. So we apply the stresses from the sides, trying to squeeze the sample, and so the 3 standard loadings which can be reproduced in laboratory. And we to perform the upscaling, we need to apply just the same experiments, but for homogeneous viscoelastic media. For homogeneous viscoelastic medium, the equations are much simpler. They're elliptic, but the coefficients over here, it's C11, C55, and all the rest, they assume to be frequency dependent. So the thing here is that we solve BO equations for each frequency independently, and we can having solved them, we can reconstruct the frequency dependent stiffness tensor for viscoelastic media. The model for viscoelastic media is much simpler. It can be used by seismic processing community, but in our what we are doing, we're trying to construct such a tensor which reproduces the same response to the quasi-static loading. And if the medium is homogeneous, the problem can be solved analytically, and that's the point. That's the way how to upscale the BO models. So what we are doing, we apply the loading, solve the BO equations, construct the solution. Then we know if we've got the particular loading for the viscoelastic medium, we can construct the solution which would depend on the stiffness tensor, linearly depend on the stiffness tensor. And then we resolve the problem and reconstruct the components of the stiffness or compliance tensor whatsoever. Yeah, that's how it works. And what we are doing to solve the BO equations. So as I told before, we are using finite differences to approximate the solution, and then we finish up with some matrix and some system of linear algebraic equations which have to be solved. And the problem is complex unsymmetric. It's incomplete rank actually, because we actually solving Neumann problem here, and but the matrix is sparse, and the pattern of the matrix is always the same regardless of the frequency. So we've got the elliptic part of the matrix which completely independent on the frequency, and then we add a diagonal matrix, Elmas diagonal matrix, which depends on the frequency. And that's quite a nice thing about all these equations, because if we use direct solvers to solve the problem, like those implementing in Intel MKL Pardiza, when we need to do some so all these solvers are using some preprocessing, and this preprocessing is always the same. It can be applied only once because of the same pattern of all the matrices. And these are the estimates of the RAM usage and total time for preconditioning, pre-processing, factorization, and solution. So as you can see, the problem of 1,000 by 1,000 grid points can be solved in just 10 minutes. So it's quite nice, and it's a total time. If we are talking, which means that we are solving it for 3 different right-hand sides, for 3 different loadings. And then we of course we tried to test our algorithm over the analytical solution. So for homogeneous medium it was quite nice, and we can estimate the frequency dependent stiffness tensor, which means that we can reconstruct the p wave. We can reconstruct the velocities of seismic waves and attenuations. And you can see that the attenuations analytical attenuation increases in homogeneous case, in the case of homogeneous media, but the quasi-static estimation not, because it comes from the discrepancy comes from the equation. The analytical approximation, analytical estimate here was obtained from dynamic bioequation. So we cannot just see this increase in the attenuation in a quasi-static state. It's not the problem of numerical simulation; it's a problem of the model. It's well-known fact about it. So next, what we try to do, we consider the layered media for which the estimates of the wave propagation velocity and attenuation are known, and we try to match them. So first of all, we played with the grid step size, and we decreased the grid step size and see and observed the quite a nice convergence of the results for different loadings. We obtained different values of the attenuation, p wave attenuation, but it converges to some stationary point when we decrease the grid step. And next, what we did, we either increased we fixed the geometry of the model and increased the size of the model to show that the results depends on the size of the homogeneity of the size of the layer, and we can see it quite clearly that the frequency dependence is completely different for different models when we increase the size of the model. And if we fix the sizes of inhomogeneities and increase the number of the layers, we see quite a nice convergence to the results, to predicted results. And of course, all this layered media is quite nice, but what we need what was our goal was it was an ability to estimate the wave speed and attenuation in if wave propagate through the fractured poroelastic medium field, where the fractures are filled with a soft material. And we did it using this approach based on quasi-static simulation and based on dynamic simulation of wave propagation through such a media. And the quasi-static estimates are lines over here, and the dynamic estimates are based on the dots over here. So we simulated wave propagation with a quite a high frequency, and then we see quite a nice correspondence between the results. So that's pretty much it. Let me conclude that we suggested an efficient approach to solve the bioporoelastic equation in quasi-static state and estimate and upscale the elastic properties of the media, of the poroelastic media, and construct the viscoelastic, very simple viscoelastic model, which gave us the same response to the quasi-static loading or low frequency loading. That's pretty much it. Thank you for your attention.
Thank you very much for your presentation. Are there questions? Any question? Just to check, can you hear me?
Yeah, I can hear you.
Yes,
At least I can hear you.
Okay, because I'm having problems with my camera, so I was a bit worried. Well, there are no questions, so I think we can move to the next presenter. Let's check. Just a moment. Okay, no, there is no possibility to. Okay, the next presenter is still Vadim Lisitsa, presenting a paper with the title Poisson Solver for Upscaling the Physical Properties of Porous Materials.
Yeah, thank you once again for the introduction and for the inviting me here. So my next talk is still about upscaling, because well, what we are doing in our lab is actually the lab is called the Digital Rock Physics, and the main point of our research is the numerical upscaling of physical properties of rocks, which are actually porous materials, of course. And that's why we are doing quite a lot of numerical stuff on that. And the Poisson solver, in our opinion, the Poisson solver is quite a key well, the main algorithm which should be implemented efficiently to do numerical upscaling. And let me say a few words why it is so important. Because if we try to upscale physical properties of rocks, we actually have quite a lot of scales. And in our case, microscale means the scale of the pore, and then we can have mesoscale at the scale of the core sample, which is about a few centimeters, and then macroscale is a scale of the reservoir. And going from each scale, from one scale to the other scale, we face with the problems which somehow related to the Poisson equation. And first of all, of course, the simplest example is the upscaling of electric resistivity, thermal conductivity, or diffusion coefficient. All of these guys are upscaled based on the solving of the Poisson equation. If we're talking about electric resistivity, then we just have to solve Poisson equation directly. If we're talking about thermal conductivity or diffusion coefficient, this upscaling is based on the limiting case when we go when time goes to infinity, and we still finish up with a standard Poisson equation with some right-hand side or boundary condition, whatever, but still we have to be able to solve a Poisson equation in a very, very, very complex model. It's not just a standard, rectangular domain or whatsoever. It's a model where we've got a lot of pores which might be connected or not connected, and a lot of different minerals in there with different resistivity, and there is the ratio of the resistivity inside of the fluid inside the pore and the resistivity of the matrix is several orders of magnitude. So it's a extremely ill conditioned problem and hard to be solved. So moreover, if we're talking about, for instance, reactive transport at the core scale, at the pore scale, and we try to upscale it, we need to come from Navier-Stokes equation to Darcy equation, where we've got permeability. and to upscale the permeability, to obtain the permeability at the reservoir scale, we have to solve Navier-Stokes equations at the pore scale, and to solve it, we typically apply projection method, where we have to solve the Poisson equation for the pressure. And once again, if we're talking about upscaling of seismic attributes, we need to solve the static the static state elastic equations to obtain the elastic moduli at the mesoscale and or at the macro scale. So, and even though it's not those equations are not entirely the Poisson equation, but they are the same in their nature, the elliptic equations, and we have to solve it in the extremely complex domain. So once again, what we try to do, we try to solve Poisson equation in a domain with extremely complex geometry and an extremely complex topology, with a lot of connected bodies or not connected pores and things like this. But the main thing here, which I have to point out, is that in all this statement, either if we are trying to update the electric resistivity and try to solve the Poisson equation for electric potential, or either we try to solve it for the pressure, the thing here is that the boundary condition, if we are talking about just boundary conditions between the interfaces between the pore and the matrix, we always think of Neumann boundary conditions, not Dirichlet. And this helps us a lot to develop an extremely efficient solver. So once again, where we get the models from? The models in digital rock physics, the model came from CT scan, micro CT scans. So these are pictures which are segmented, and then we finish up with a already grid-based model. So all we know about the model is that, so we know the model on given at some grid. The voxels came from the resolution of the scanner. We cannot get extremely precise description of the interfaces in there. So we don't need to go, and moreover, the model is extremely complex. So, and then if we try to go to finite element approximation, we will stuck there forever trying to match the interfaces correctly. So the bad thing in our opinion, if we are talking about digital rock physics, is to use finite differences of finite volume approximation. And if we're talking about Poisson equation and, I don't know, solving, for instance, for electric potential, we can apply just simplest finite difference approximation here, because the resolution is already extremely fine, and we don't need to increase the order of approximation or whatsoever. That's the other point and the other feature of digital rock physics. The grid which came from CT scans is already fine enough to describe the geometry of the model and to approximate the equations. And we actually checked it, and it's there is no reason to increase the order of approximation here. So okay, it's quite easy to approximate the Poisson equation using finite differences, and then we need to solve the system of linear algebraic equations here. And what we are doing, what we are using here is, of course, it's a BCG stub. It's just a standard tool. But the main thing here, of course, is the preconditioning. And the standard approach to precondition Poisson equation is to use multigrid. But the problem here in our simulation is the complexity of the domain geometry. And using the multigrid, using the mesh coursing the mesh would cause complete, well, the model which we get on the coarser mesh would have completely different topology. The pore space on the coarse mesh would have completely different topology and completely different. Thus, we would have completely different solution which have nothing in common with the true one, and the operator on a coarse mesh would have nothing in common with the operator on a fine mesh, and it might not be the preconditioner at all. That's the main problem here. So we decided to do the following thing, which is quite nice if we're talking about Poisson equation with Neumann boundary conditions. Even if we have complex topology, we apply the fast Fourier transform in the direction across the main current. If we're talking about upscaling, we applied the electric current from two opposite sides. We applied the potential difference at the two opposite sides, and the four opposite sides are free from external current. And we applied the Fourier transform with respect to those two directions, normal to the main potential change. And in this notation, and then we solve. We've got a series of 1D problems along the main current direction, and we solve it using standard. So to solve it, we just use it explicit using direct solver, and this and how it works in GPU implementation. Why it works very fast? Because we use QFFT to apply Fourier transform, and then one single thread solve one single 1D problem. So it's completely parallel if you implement it on GPU. And then we apply inverse QFFT. And the thing here is that we don't need to do CPU to GPU transfer at all, and that's why it works extremely fast. And these are a few examples on that. So the thing here that the algorithm is implemented on a single GPU. So the maximum sample size which we can deal with is 400 cube voxels. And if we use this sample and we try to solve to solve Poisson equation for such a sample, in average the time per one iteration is about 1 second, and the number of iterations depends on the difference between the matrix conductivity and the fluid conductivity. And the higher the difference, the more iterations we need, but still we never need more than 300 iterations. So it means that we can solve the Poisson equation for such a complex geometry, complex topology of the pore space for the samples of up to 400 voxels cubed in no more than 5 minutes. So it's quite a nice performance. We applied this algorithm to estimate the change of the electric resistivity or actually formation factor of the core samples, which came from the real lab experiments. These are carbonate samples of carbonates, which were, and we've got the CT scans of these samples during CO2 injection and the dissolution of the matrix. And then we perform simulation we solve Poisson equation and estimate the formation factor at each stage of the CO2 injection, and you can see that the formation factor indeed decreases because the pore space gets bigger and bigger, and the path of the current gets straighter and straighter. And as I told before, it was the samples was about 400 by 400 by 400 voxels, and we solved this, and each simulation took us about like 5 minutes or something. And that's pretty much it. So let me conclude. What we present is a new implementation of GPU-based implementation of the Poisson solver, which allows us to estimate a wide range of physical properties of digital rocks. And the standard execution time is about 5 minutes for the samples of up to 400 voxels. That's pretty much it. Thank you for your attention.
Thank you very much, Vadim. Are there questions? Any question? Okay, apparently we don't have this, but I have a small, short question. Because you provided us results in terms of timing, but if I am correct, you didn't provide the specification of the hardware of the GPUs you have utilized, because it can be very different depending on the GPU. There are
definitely. It's a good question. So this particular one, these particular experiments were simulated using GeForce RTX 2080. So it's not a GPU. It's not those professional GPU installed in clusters. It's just a GPU which is installed in a desktop.
Yes.
And of course, it's not the most powerful one.
Yes, I know. Well, it's not bad, but you said 2080?
Yeah, 2080.
Well, it is relatively recent.
Yeah.
Okay, thank you very much for the presentations, for both presentations. And let's check if we have the last presenter. The last paper is properties of multipyramidal elements. Is there here any? Okay, so the presenter, the name of the presenter, I couldn't see.
The presenter will be the second author. My name is Todor Todorov.
Because
maybe
I
begin with my presentation. Dear colleagues, I'm glad to present to you new results in the area of computational geometry.
Okay, please go ahead. No, you did set the name, probably.
Yes, I said my name. My name is Todor Todorov. Look at here.
Okay.
This is my name. I'm the second author.
Yes. Okay. I meant in the system. Okay. Please go ahead.
Most of the papers on the finite element method deal with numerical analysis and error estimates in numerical approximations of the solutions of the eigenvalue and boundary value problems. But the successful application of the finite element method depends on the quality of the finite element meshes. The quality of meshes is of significant importance, especially when the isoparametric multigrid method is applied to solve elliptic problems in domains with complex geometry. The multigrid methods require successful refinements of the initial triangulations. That is why the stability of the sequence of successive triangulations is a crucial point for the convergence of the multigrid approximations. The theory of the finite element meshes and advanced discretization methods can be considered as a separate scientific area closely related to the finite element method. We emphasize that the finite element meshes have been applied for computer graphic simulations.
Excuse me, Todor, excuse me.
Yes.
Now you are showing us a list of references. Is it on purpose or is
yes,
it
I talk about these references and a motivation about that what I do. That is why the references are on the screen. Look at this is the slide number 2.
Oh, perfect. Thank you very much.
Here is the slide number 2. But I want to begin my presentations with the motivations to what we are going to do. That is why the references
Consider
are
that you only have 15 minutes.
The efforts of various authors have been devoted to different refinement strategies. Hannukainen and al. 10, and here is the reference of Hannukainen and al. 10, Vidrigo and Rivara 3, and Perdomo and Plaza 20 focus their research on the longest edge bisection methods. The bisection methods have been generalized to arbitrary section methods by Korotov et al. 12. Maybe it's not Korotov but Karotov, or my pronunciations would not be clearly correct. Other refinement strategies have been demonstrated by Luo et al. 13, Petrov and Todorov 17, and Verstraeten and Kosinka 22. Arteaga et al. 11 present recent advances in the theory of the finite element meshes. Subdivision techniques in multidimensional Euclidean space have been studied by Brans et al. 6, Pascucci 19, and of course Petrov and Todorov 16. The pyramidal elements are relatively new finite elements. In the three-dimensional case, they have been created by Bedrosian 2, reference number 2, in the early 90s. The pyramids play the role of transitional elements between structured and unstructured finite element meshes. The pyramidal elements have made possible the development of the hex-dominant meshes considered by several authors, see references 14, 21, 24, and 25. The applications of the pyramidal elements for constructing hybrid meshes has been described in references 4, 7, 8, and 9. Mathematical models based on composite hybrid meshes have been developed in 14 and 15. In the three-dimensional domains, the conforming coupling between hexahedral and tetrahedral meshes does not require complicated transitional elements. The pyramidal elements assure conformity in a natural way. This construction has been applied by various authors. See, for instance, the paper by Yamakawa and Shimada 23. The simulation is completely different in the higher dimensional spaces. A tesseract pyramid cannot be coupled directly with an arbitrary hexatheron, since all facets of the hexatheron are pentatops, but the pyramid has not got any simplicial four-dimensional facet. Therefore, the hybrid meshes construction in higher dimensional spaces needs a different approach. New transitional finite elements should be developed. And now we are talking about the major contribution of the paper. The paper is devoted to the geometrical foundations of the finite element method, and in particular the theory of meshes. One of the fundamental problems of the finite element method in an arbitrary n-dimensional Euclidean space is solved in this paper. New K-pyramidal elements are obtained. Their properties are discussed too. Specifically, in the five-dimensional space, new cubic bipyramids and bihexatheron elements are developed. A conforming coupling between hypercubic and simplicial polytopes is demonstrated. Bipyramidal elements in arbitrary high dimensional space are uniformly refined. Plenty of new notations like k-pyramidal elements, conforming chains, etc., are introduced. Here we introduce some basic definitions. In this slide, we defined the Freudenthal quadruple class, the multidimensional hypercubic pyramid, and the n-dimensional bipyramid. An example of a quadruple element in the 5-dimensional case is presented. And this is the Freudenthal simplicial class, which is written over here in example 1. This is an example in the 5-dimensional case. In this slide, we see a set of reference elements. The line segment bipyramid is located in the upper left corner. But actually, this is a tetrahedron. The square bipyramid is placed in the upper right corner over here. And the cubic bipyramid is down left. This is a cubic bipyramid. The two-dimensional pyramid is the well-known triangle, but a two-dimensional bipyramid does not make sense. Therefore, we begin with the three-dimensional case. From the definition 5, with n equal to 3, we see that the three-dimensional bipyramid is a simplex, but this is valid only in the three-dimensional case. The square pyramid is a transitional element in the interface subdomain between structured and unstructured meshes. Multigrid methods require stable refinement of all elements in the coarse triangulations. The optimal refinement strategy for the square pyramidal elements has been described by Ainsworth and Fu. In the three-dimensional case, this is over here. This refinement strategy is demonstrated over here on the top of the slide. Similar results in the four-dimensional case have been obtained by Petrov and Todorov, our team. In the second row, we observe conforming coupling between cubic pyramids and bipentatops. The pyramids have been drawn in red and the bipentatops are in blue. This color legend is used both in 3- and 4-dimensional cases. And here we can see the conforming coupling between bipyramid and cubic pyramid. But this is the same situation in the 3-dimensional case, where the 3-dimensional bipyramids are presented in blue. Here we define the n-dimensional K-pyramid and introduce the very important notation conforming chain. The whole spectrum of the reference transitional elements in the n-dimensional Euclidean space are defined explicitly in this paper, and you can see it in this slide. The set of n-dimensional hypercubic, n-dimensional simplex, and all transitional elements that assure a conforming coupling between them is said to be a conforming chain. This is very important notion, and we introduce this notion for the very first time in our paper. In this slide, I present the main results in this paper. The conforming chain is found in the n-dimensional case. The transitional elements are presented explicitly. A uniform refinement of the transitional bipyramids by quadruple Freudenthal elements is obtained. The uniform refinement essentially reduces the computational complexity of the integral computations in such elements. Additionally, the new reference elements are also triangulated uniformly. On the other hand, the n-dimensional K-pyramid and the n-dimensional K+1 pyramid share a n-1 dimensional K-pyramid. This is the conforming chain over here, but in this sentence is a very important property because both of these share this one. And we can see this in further examples. In order to get a better illustration of the theory under consideration, we need an example in a higher dimensional space. Let us consider for the very first time a 5-dimensional example. In this slide, you see the unit Penteract partitioned into canonical pyramids. This is the unit Penteract. Penteract means 5-dimensional cube. You can observe that both Tesseract pyramids share a cubic pyramid. The first one is presented in red. The second one is in blue, but they share this cubic pyramid over here. Continue with the 5-dimensional example. Here is the conforming chain. And each conforming chain contains of so many elements, which is the number of the dimension of the space. Here we have 5 finite elements. And both of them, this couple, share a tesseract. This is the penteract, but this one is tesseract pyramid. Both of them share tesseract. And this is very interesting because they share the first one from the second chain, from the 4-dimensional chain. Here is the tesseract, but this is in the 4-dimensional case. Further, tesseract pyramid, this one, and the cubic bipyramid, this one, share cubic pyramid, which is the next in the low-dimensional case, in the low-dimensional space. Continue with the couple between the green one and the blue one. They share square bipyramid, which is written over here. And finally, we have to clarify which pentatop, which polytop share this one and this one. And actually, they share pentatop. In other words, all these 4 are included in this 5-dimensional space. Thus, we obtain the 5-dimensional conforming chain. I think that this 5-dimensional example presents the theory in the best way. But to be more comprehensible, I want to present low-dimensional cases. Let us consider a conforming chain in the 4-dimensional case, which is presented on this slide number 12. We have to do a conforming coupling between tesseract and pentatop. And we need only 2 transitional elements, which are cubic pyramid and square bipyramid. And at the beginning, the tesseract and the cubic pyramid obviously share a 3-dimensional cube. But considering the next couple, the cubic pyramid and the square bipyramid, they will share something which is written in the 3-dimensional case. In other words, this is written in the 3D conforming chain. And this is a square pyramid. Both of these share the square pyramid. And finally, this couple on the right-hand side share a tetrahedron, which is written down in the three-dimensional space. Actually, the four-dimensional case, the four-dimensional space is very easy comprehensible, and it is not so interesting case, but I present it because I want to all of you to understand what I'm talking about. And here, let us consider the three-dimensional case. Obviously, the cube and the tetrahedron cannot be coupled directly. We need transitional elements, but in the three-dimensional case, this transitional element is only one. This is the square pyramid, which is presented in red over here in this slide number 13. And at the end, the most simplest case, this is the two-dimensional case. The cube and the simplex are connected directly. No transitional elements over here. But I want to emphasize that the whole chain has so number of members, which is described by the dimensions of the space. In the two-dimensional case, the whole chain has only two terms, two representatives. In the three-dimensional case, there are three. In the four-dimensional case, there are four. And finally, in the five-dimensional case, the whole members are five. Obviously, in
you should go to the conclusion.
Case, please.
Oh, you should go to the conclusion because
yes, I haven't. I don't think to present a conclusion, and I go to the end of my presentation. And actually, what will be in the n-dimensional case? The conforming chain will contain n number of polytopes. And that's all in my presentation. If you have any questions, you are welcome.
Okay, so any question? Is there any question? We don't have questions, but I think it's really interesting. I knew about the monodimensional, bidimensional, three-dimensional finite element method, but honestly, I didn't know about this multidimensional perspective of the finite elements method. But can you mention applications of this, like five-dimensional?
Yes, this is a very good question. What will be the applications? Let me talk about not multiplications, but I've lost the word here. When we have two particles in the influence of two particles in square. This influence of two particles in square is described by Schrodinger equation in Tesseract. I present Tesseract over here. Just a moment. Find it in the left upper corner. And this Schrodinger equation is an elliptic equation which is solved by multigrid methods. And this is a very sensible applications. Moreover, let us imagine that two particles have influence in cube, which is a very real situation. Then the model, the mathematical model, will be Schrodinger equation in Tesseract. This is six-dimensional cube.
Six-dimensional.
Six-dimensional.
Fascinating.
And
very interesting.
Here.
Okay, thank you. See, yes.
Okay, let me finish. There is a paper of Korotov. Look at this paper of Korotov. Not this one, just a moment.
12.
This was a paper of Korotov in which this is longest edge by section in n-dimensional space, but there is another paper of Korotov. I don't see it. That's one. Number 6, which presents all applications of the finite element method in multidimensional spaces.
Higher dimensions. Very
yes,
interesting.
Multidimensional spaces. And here we talk about n-dimensional spaces and applications of the finite element method in the higher dimensional spaces. This paper makes the beginning of new era in the applications of the finite element method. And this is about the applications. Most of them are in physics and in engineering.
Very interesting. Thank you very much again. And I also would like to thank all the presenters, obviously, and maybe someone is already at the coffee break. Is there any coffee break?
Okay, thanks for all of you.
Thank you.
Attention.
Thank you for your participation, for your contribution today. And in 5 minutes, we have another session. So goodbye for now. Okay, I think we can start also this presentation, this session. This last session. Good afternoon to everyone. We have here 4 papers, and for the first paper, is there any presenter for the first paper? Let's check. The first paper is a composite function for understanding the bin packing problem and taboo search. Is there anyone for this paper, presenting this paper? Okay, so we can skip this one, at least for now. And anyone for the second paper? Raffaele D'Ambrosio and Carmela Scalone.
Hello,
Carmen Scalone.
I'm Carmen Scalone. Yes, I'm here to present. Can I share my screen?
Well, I think so, yes, because actually the first presenters didn't show up. So you can start with your presentation. The title of this presentation is Asymptotic Quadrature Based Numerical Integration of Stochastic Damped Vectors. There is a noise, I don't know why.
Can you see my screen?
Excuse me.
I can see the
Excuse me.
screen.
Can you hear me? Can you hear me, please?
Yes, we can hear you.
I am Vanessa Landero. I am the first expositor.
Okay, you are the first because we had actually.
Sorry.
For some reason you couldn't.
I interrupt?
No, it's okay because we. No. Okay, I think now it's much better to continue with this presentation. We start with the second presentation, then the one we skipped with the second presentation. So sorry. So you can consider that you have 15 minutes in total, including the questions.
We're going to bother the boss, but Natale is online, you know?
Yes.
Can I start?
Yes, you can start.
Okay, so thank you very much for the introduction. Let me just mention that this talk is based on a joint work with Raffaele D'Ambrosio, also from L'Aquila. And we are interested in stochastic oscillators. And as we can see, for instance, in the nice book by Moshe Zitterman, many several examples of stochastic oscillators are obtained when we introduce a noisy component in a deterministic model of oscillator. For instance, we can have additive or multiplicative noise, random frequency, random damping, etc. And we are interested in numerical analysis issues related to stochastic oscillators. And essentially, we have 2 main issues in literature. We can have the preservation issues. We test the preservation attitude of a numerical method of quantities which we know they are conserved in the model analytically, essentially. Or another issue, which is essentially the topic of this talk, is to design specific numerical schemes for a particular considered type of oscillator. So in this case, we present a second-order stochastic differential equation which describe an harmonic damped oscillator driven by a random Gaussian noise and a time-varying force G. we can write equivalently this equation as a system of two equations of the first order, and we suppose that this function g is the driving function of the oscillator is highly oscillating itself. We suppose that it has the form a of t, a function of t, multiplied by the exponential of I, which is the imaginary unit, sigma, which is the frequency of the force, and a function of t, which we denote by h of t. And this is very typical in the deterministic model. We can see, for instance, the work by Condon, Isserles, and Norset. And we start essentially writing via the variation of constant formula our equation in its integral form. We aim to provide a discretization of this equation, and we start with the stochastic integral, which we discretize as usually, essentially. So the remaining term is the term involving the time-varying force, the highly oscillating force, which and we consider essentially a technique used also in deterministic, widely in deterministic models, which is the asymptotic expansion of the highly oscillating integral. So essentially the approximation of such integral is given by the truncation of the series. In our approximation, we will truncate at the second order, and when the integrand function is highly oscillating, we have a good convergence. We have a good approximation of the interval with such truncated series. For more details about the asymptotic series, we have the reference of the work by Isserles and Norset, for instance. And so we have a full discretized procedure, and so we can test our numerical method, for instance, on a very popular stochastic oscillator model in the literature, and we will test our essentially we will consider our oscillating function, driving oscillating function, for h of t equal to 1, so constant essentially, and h of t given by the very simple second degree polynomial of t. So in our experiment, in this case, sigma, in this case we choose sigma equal to 80. So we have a good oscillator, a good oscillating phenomena in the force, and in this case h of t is polynomial. We find that in this plot we plot the mean square error in the position with respect to the step size, which is the blue line, and the red line is the line with slope 1. So we have a good estimated rate of convergence, 1, we can say. And so we test also for h of t equal to 1 and sigma 60. So essentially the rate is the same. It not depends on the function, on the parameters. And also we have this case in which the oscillation is very high. We have sigma equal to 150. So we can say that the full discretization of the model, given by essentially via starting from the variational constant formula, discretizing the integral, the stochastic integral as usually, and introducing this procedure of truncated the series describing the behavior of the highly oscillating integral can be a good procedure for this kind of oscillators. If you are interested in, we are deeply studying stochastic oscillators, I give you some references. So I can conclude now, and thank you for your attention.
Okay, thank you very much for your presentation. The questions? Any question concerning this presentation? Okay, we don't have questions. So now should be the turn of the first presenter that we skipped before. So thank you very much again for your presentation, Carmen. And,
thank you. Bye.
Thank you.
Thank you. And now we have the paper, a composite function for understanding bin-packing problem and taboo search. Words self-adaptive algorithms. You can start. You have 15 minutes.
Thank you. Can I expose after that the another person, because I have problems, technical problems, please.
Okay, you have then technical problems. Natalia, given that you have here some experience in technical problems.
Prof, the first team is in a physical room.
So we can move to the third presenter, Juan Antonio Arias Lopez, who is in the physical room, yes. So in this case, okay, the paper is computational issues in the application of functional data analysis to imaging data. And I think he can start the presentation in the physical,
can you hear me?
Conference room. Yes.
Yes.
So you can hear me and you can see me, I guess.
I confirm that you can see
and if I do this, yeah, sure.
Perfect.
All right. So shall
About
I?
15 minutes in total, including questions and answers.
Sorry, shall I begin?
No. Yes. You can start. You can. You have 15 minutes in total, including questions and answers.
Yeah, I think we are a bit ahead of schedule because I was planning to do this by 6:15, but it's all right. So, well, thank you everyone who has joined us presentially, especially this Mr. Hendricks, who is the only one here, and you everyone who joined us virtually, and friends, colleagues, and family. So let's begin with the presentation, which is an article and part of my doctoral thesis. Well, the name, as you said, is Computational Issues in the Application of Functional Data Analysis to Imaging Data, in particular to neuroimaging data for Alzheimer's disease. And this is a study that I'm carrying out with my two supervisors, Carmen Cadarzo and Pablo Aguiar, both from University of Santiago de Compostela. So without any hesitation, so first, given the scope of these conferences, in which mostly we're talking about mathematics, computer science, I would like to start my presentation with a bit of a background on the disease that I'm working on. I'm working on Alzheimer's disease, which is the most common neurodegenerative disease in the world right now, and together with Parkinson's. And it's also the responsible for most cases of dementia worldwide. It's been called a slow motion pandemic, not only because it develops very slowly, but also because it's present in one of the most vulnerable sectors of our society. And it characterizes itself by being a progressive neurological disease, which produces damage mainly to the hippocampus, which could be this red area marked here, and temporal in blue and parietal in less extent in green cortices. So this impairment, as many of you might know already, affects mainly memory, but also orientation, emotion regulation, and in late stages of the disease, it may affect to many other cognitive processes. So by now we don't have a cure or anything that might look like a cure in the following years. We just have treatments to slow disease progression, which are called the neuroprotective treatments. And recent articles suggest that maybe Alzheimer's disease might start between 20 to 30 years prior to the first visible symptoms. So we have to keep in mind that we might be treating a very serious disease when it's been already working and making damage for maybe 20 to 30 years. So it's usually irreversible at that stage. So what the neurobiologists at this stage are trying to do is to identify the disease in an early stage when there are no observable symptoms and try to chronify it, just to apply neuroprotectives and leave the patient in a more or less healthy state of other reasons not related to Alzheimer's. So this is for the disease. Now for the data that we work with, there are several kinds of data that we can use, behavioral, but the most useful, I would say, and also the most common are neuroimaging. There are several ways to obtain images of the brain. Some of the most popular have been suffering from problems of bias, like fMRI, magnetic resonance imaging. So in my thesis, we're working with a well-established technique, which is 18F FDG PET, or positron emission tomography, which uses a radioactive tracer, which is 18F FDG, radioactive particle similar to glucose. So we measure how different regions of the brain consume this isotope of glucose, and thus we can obtain a relative measure of brain activity, of metabolic brain activity. So we should expect that Alzheimer's disease AD patients will display a reduced FDG PET values. So for example, in these cases, it would be the green and blue areas, whereas orange and red areas would have a higher activity. Well, just for, I must say this, neuroimaging data is usually, it's naturally three-dimensional, but it's almost impossible to work with three-dimensional data for these things. So we usually work with two-dimensional slices in one of these projections. For example, in my case, we usually work with the axial projection. This is a cut of the brain. This is the frontal part and parietal part. For example, this area is the hippocampus. So, yeah, just to be in the same page. And sorry for the noise. There must be a demonstration or something. So this is the imaging data that we usually have for Alzheimer's diagnosis. The problem is that we don't have the methods or the capability for an early diagnosis of Alzheimer's, and thus we have these problems that we cannot offer an effective treatment to the patients. So my thesis is dedicated to looking for new statistical methods which can give us better insights on the data that we already have. We have neuroimaging data, and what we want is an early diagnosis. One of the proposals is the use of functional data analysis. I will develop this in the following slides, especially simultaneous confidence corridors, also known as simultaneous confidence bands, which is a theoretical approach proven to be efficient in Wang et al. 2020. And as far as I know, we in Santiago are the first ones to apply this methodology to a practical case. So what are we looking for? We are trying to detect the areas which, comparing Alzheimer's disease versus control groups, are suffering from hypoactivity, which could be reasonably neural loss. So if we manage to detect this neural loss early and accurately, this is important because there are other tools used nowadays that can detect it early but not very accurately. So that could be a lot of false positives. If we can manage to do this, that would be a huge step in Alzheimer's disease treatment and diagnosis. The tools, which is not very important here, but we use MATLAB for image preprocessing and mostly R, the statistical package for the statistical analysis, obviously. And the goal of this project, like this paper that we're presenting here, is to analyze and compare brain images with functional data analysis, that's what we said, but also, and this is the main goal of this article, to evaluate computing times of this process, because if we can do this, but the time that we need for it is just absurd, like maybe weeks, because this can happen with functional data analysis, where with cumulative effects, you can end up having needing weeks of your computer working to obtain any result. So let's get into detail now that we have this background. And I'm afraid that in order to do this, we will need to use mathematics. Functional data. So for those of you who are not familiar, functional data analysis is a relatively new field of statistics, kind of complicated for people like me who are biologists, because they live in these mathematical spaces, like the, well, anyway, field of statistics which works with data in the form of functions. Like, for example, this is an example not related to my study. These are rain precipitations on a given day, and it works like every year, every function is a year. So this could be, for example, the functional mean for a weekday and the functional mean for a weekend. So basically, when we work with functional data analysis, it's not the data, the single data, that is the minimal unit, but it's the function. So one subject, one participant, either control or Alzheimer, would have one function, because it can be, well, as I said here, these methods can be extended from functions to images, which is basically the same, but it's a function in a two-dimensional space. And in this case, we are working, well, we consider that single points, single data are only realizations of the underlying function, which is what we are trying to obtain. Traditionally, these methods were, well, there is a method for this, which is called SPM, statistical parametric mapping, but it's kind of rudimentary, let's say it this way, because they rely on the mass univariate approach. So given, for example, a brain slice of 79 times 95 pixels, we would have, I think it's 7,905 pixels, and we would be carrying out one t-test for each pixel. So it's not very difficult to see that first we are going to suffer a problem of multiple comparison. We're going to have a lot of positive results that are not really positive. Also, we are ignoring the spatial correlation completely. Yeah, we are just doing one t-test per pixel, and that's it. And also, for example, we can see it here in this little pixel, which only half of it is part of the brain and the other half is empty space. We suffer from a leakage of information in complex data structures, and a brain is, of course, a complex data structure. So what happened when we try to obtain this simultaneous confidence corridor, this functional data method to brains? First, we need like a matrix in which we can do our measures or functional regressions. So we use bivariate splines over a Delaunay triangulation, which is something that I'm going to explain in the next slides. And then we compute the mean function and the associated confidence band in the form of images. This is going to be much easier to understand when we see the next slides. So, but what we see here compared to SPM is that we are solving the problem of leakage in complex structures by using Delaunay triangulations, and also when we are using images as functions instead of a series of independent pixels, we are also solving the problem of multiple comparisons and also the spatial correlation. So this could be like the end of the project. This would be the images that we want to obtain. So for example, here, just to understand ourselves and to be in the same page, we'll have a control group and the Alzheimer's group. In the middle, the mean function. Instead of a function like here, we are now working in a v-dimensional space. So this is actually a function, but representing a slice of a brain. And considering this legend, you can see that this is the lower confidence interval in the form of an image and the upper interval. So we could say that at any given point with a given percentage of, well, with a given alpha, you can say with 95% of probability that the activity at that point is between, let's say, 3.5 and 3.8, with a mean of 3.7, for example. And the same with the Alzheimer's. And then what we can do, this is a one group setup, but this method is also useful for a two group setup in which we overlay the two series of images, calculate the intervals, the simultaneous confidence corridors for the difference between the images. And so we can compute which regions are suffering for neuronal loss or gain, which is something that in biological terms don't have any meaning, but in mathematical terms do. So for example, we could say that these regions in blue would be suffering from neuronal loss in the Alzheimer group compared to the controls. But this method, is it worth the computational effort? Because we can use SPM, and that would be easier and cheaper probably in computational terms. So the goal of this study was to do a series of replications and simulations and loops to calculate the computing times for the one sample and for the two sample approach. First, the Delaunay triangulations, I was talking about it just a few minutes ago. Definition: these are triangles that are created by the union of different vertices, and no vertices fall inside the circumcircle of that given triangle. So this way you can see here that in the regular areas of the brain, it's quite an easy, just like squares, it's easy. But if you go to the more complex areas of the brain, you have a more complex and detailed structure of points where the regression is going to take part. The authors, Wang et al., suggest, well, the first authors of this method suggest an n is a degree of fineness of this triangulation, and n of 8, but we can also compute it n 15, 25, and so on and so on. So one of the first things that we had to do was to compute timings for this, and we realized, well, it's a very reasonable timing. The author suggests an N8, but we can see that higher values like N25, like this, could be also sensible to work with. Then for the one group SCC, now we're working with simulated data because it's much easier. We obtain the mean function, upper and lower SCC, and
you should go to the conclusion now.
All right, I'm moving fast. I'm already arriving to the conclusions. So these are the computational times. Also, higher values for a higher triangulation degree of fineness, lower for the lower triangulations. Again, Wang et al. Recommendation of an n equal 8 is, well, we can go for an n 15 without much change. Now for the two group SCC, we did exactly the same, a simulation and then the calculation of the computing times. Extremely stable. We can again skip this recommended n equal 8 and go to the n equal 15 because it pays. So conclusions. This methodology, even though it's just in the middle of its development, is quite stable for comparisons of very large number of participants. We're talking about maybe hundreds of them because functional data analysis is prepared for using a big number of participants, but it is affected by cumulative effects when we change the triangulation complexity. That would be the parameter that we have to pay attention to. But still, a triangulation fineness of n equal 15 would be reasonable with computational times that should be sensible for any computer. But now limitations and further research. The limitation of this method is that it's unable to classify one single patient. This is being used for blocks of patients for basic research in order to look for the difference between Alzheimer and controls. And so the preliminary results are positives, but we still need to prove it better than SPM. So for the research, this is what we are currently working on, maybe for the ICCSA 2022, God knows, is to compare results using SPM and the proposed results with functional data and demonstrate mathematically that the ones with FDA are better. And finally, the optimal point would be to develop some sort of algorithm for an automatic classification of images in pathological or healthy in order to aim for early diagnosis of this really serious condition. So, well, any further considerations on the code with Python, MATLAB, R, and code, loops, functions, and anything can be found in my GitHub repository. And if anyone wants to make any questions now or in the future, I'm open to suggestions and to answer any email.
Thank you very much, Johan. We have time for just one question in case. Is there any question? Okay, there is also a significant noise from outside. No questions apparently.
It's too late for questions, I think.
Please?
Yeah, I mean, it's too late. I think I'm the last.
No, well, actually, this is the last session. So, then just a very short question, because you didn't mention you said that this method is very expensive from the computational point of view compared with other methods, but you didn't mention in practice how much it's expensive.
How much? All right. That's the question, isn't it? Sorry.
Yes, this is the question. Because
so
numbers.
For a regular computer in a university, in the paper there are the specifications of the computer. We might be talking for let's say 75 participants against another 75, maybe 12 hours, like for the whole night and a bit more. So it's quite expensive. If you use a server or anything like that, it might go down to maybe half an hour or 1 hour, but still quite expensive in computational.
It's quite expensive indeed, yes. Thank you very much again.
Thank you.
Now we are ready for the first paper that we had skipped before because of technical problems.
Thank you.
So I would like to introduce Vanessa Landero. She will present a paper entitled A Composite Function for Understanding Bean Packing Problem and Taboo Search Towards Self-Adaptive Algorithms. Please. You can start with the presentation.
I don't hear the presenter. Unmute the microphone, please.
Okay, I'm here. I'm here. Thank you.
Okay.
Thank you very
Okay,
much,
okay.
and thank you for your consideration about my technical problem. Sorry, I am sharing my presentation. Can you see it?
Yes, yes, perfect.
Okay.
We can see it. You can start. You can.
Okay, thank you. Okay, let me starting. The objective principle is to give the best solution to some problem. And sometimes it's necessary to apply algorithms to find the best solution. The relation between problem and algorithm has been characterized by feature from problem or algorithm. Sometimes, but also, the relation problem algorithm has been analyzed in descriptive and predictive understanding levels. In the last case, for selecting the most indicated algorithm, either predicting the best performance or tuning parameter. However, it is better to explain performance behavior besides predicting it. Performance explanation depends on analyzing and understanding factors or features that can affect it. Causal modeling formally represents relations between algorithm performance and factors or features that can affect it. So, the scientific community of different disciplines, such as combinatorial optimization, machine learning, artificial intelligence, and other fields of knowledge, has worked for describing and analyzing the experimental relation between problem and algorithm, with the objective of solving a real problem optimally. However, its analysis has been conducted in most cases in descriptive and predictive understanding levels, and it is necessary depending more in this objective in the explanatory understanding level, answering why the relation of certain problem instances and algorithm produces best solutions. Es decir, o sea, it is to say, sorry, algorithm is very good, and why it is not good with other problem instances. Why? Problem formulation. For a set of algorithms we apply case of studies from relation, and we use bin packing problem and threshold accepting algorithm. Okay, and we formulate the next problem for a set of algorithms A applied to a set of problem instances P with problem features phi, algorithm features L, the algorithm performance space Y, the algorithm performance partitions WY according to Y, and an ordered pay algorithm N partition. It belongs to WY. Find the composite function that discovers an explanation formal model M such that M represents the latent knowledge from relation between features that describe the problem features F, interest algorithm L, and provide solid foundation to explain why certain problem instances being the partition C correspond better to interest algorithm AQ according to performance space Y, and why other partitions do not correspond to algorithm AQ. So, in general terms, the composite function E consists of analyzing the experimental relation between the problem and algorithm, considering the space of feature from problem P, the space of feature L, and performance Y from algorithms during execution for discovering latent knowledge about this relation represented by explanation model M. The domain of proposed composite function E, wait a moment. Can you see it? Because I needed move with my mouse. Okay, I don't know if you can see it, my presentation. Or
no, actually, now the slides disappeared.
Okay, sorry. Okay, yes. We here. Is the composite, the domain of composite function, this composite function. So our parameters the interest algorithm first, the interest algorithm. So next, the space of problems and the space of algorithms, also a set of algorithms, apply a set of problems P, okay? And set F obtained by function if, okay? And the performance space Y, the set L obtained by function L, and the performance space Y obtained by function Y. The functions F and L perform a description process before and during execution of algorithms to obtain features that represent information about set P and A. So, means problem and algorithm, okay? The function Y evaluates the algorithms. The function Y evaluates algorithms by means a set of performance metrics. The acquisition of latent the knowledge obtained from this composite function about experimental relation between problem algorithm is formalized by means these parameters and this process, iterative process. So this function is evaluated in each iteration, obtains the values of a set of significant features, causal relations between this feature and estimation represented by sets B, G, and C. So these represent a causal model. Okay. The function FB, identifies significant features that characterize problem structure in space and algorithm searching behavior. So, for example, in case study, we have two the cases of study. For example, in case study, the data set B1 is formed by features this and the scope interest algorithm. With the objective of considering metrics known and used by scientific community describing the algorithm searching behavior, the autocorrelation coefficient and the autocorrelation length, and highlight the utility of our proposed features. These we build another data set, B2, is built with features from problem and from behavior, searching algorithm searching behavior. So with these features that autocoefficient correlation and autocoefficient length, this, okay? The data set big one in cases of study, see, are the best because we found direct causes to algorithm performance. Look that. Okay, so, and when we used another metrics, also another features from algorithm searching behavior, we can find a causal model so that represent direct causes, direct relation, cause and effect. So you can see it in this picture. The function fg performs the process of learning a causal structure. We use algorithm PC with a confidence level of 95%. See, in case studies 1 and 2, and we use the inference software Hugging. It is important to emphasize that the causal structure G1 and G2, in this case, it represents clearly the direct causes, problem and algorithm significant feature of performance scope for the algorithm original algorithm, and the other causal models did not yield relevant information about direct causes, did not yield relevant information about direct causes for algorithm performance scope with respect to algorithm behavior during its searching. These structures were considered for the next analysis. Also, this figure shows the intervals of direct causes obtained previously by function FT. Continuing with the composite function E, the function FC, referring to parameter learning algorithm counting, estimates the intensity of causal relations. And we see
Vanessa, you should go to the conclusions.
Yes.
Only 2 minutes left.
Okay. And in the review, the results, we compared the original algorithm with the self-adaptive algorithms, and we obtained best results because when these have same quality, the self-adaptive algorithms obtain best time, and when the self-adaptive algorithms have performance, we apply a non-parametric statistical test of two dependent samples, Wilcoxon sign right, and there is a significant difference. Okay, and so the self-adapting algorithms were best. The analysis of algorithms using causal models allows to study the nature of complex algorithms and to contribute to the generation of knowledge about them. This paper proposed a formal composite function for cases of study from relation between Tesseract algorithm and beam packing problem. The generated models were inferred from the observation and analysis of proposed features related to logical design and algorithm performance. Okay, and as a future work is to study the relation between beam packing problem and other algorithms, genetic and colony optimization, and so on for other optimization problems. So thank you.
Thank you very much. Thank you very much. Are there any questions for Vanessa? Any question about this presentation? No questions? Well, actually, I have a question, Vanessa. About the results. It's a question about the results. Can you hear me?
Yes.
Okay.
I can hear you.
Well, you showed us some results in which you compared the adaptive algorithm with the baseline version, the non-adaptive version, if I have well understood.
Okay.
But did you perform any comparison with the state-of-the-art algorithms for this particular one-dimensional beam packing problem? Because I think that the comparison with the baseline algorithm is not very significant. It's interesting, but you know, an adaptive version works better than a non-adaptive version of the same algorithm usually. So my question is if you did any comparison with state-of-the-art algorithms for this type of problem, or if you are planning to perform this type of investigation. Please.
Okay. Yes. The methodology that we use can be used to another problems. So another algorithms. The difference. The principal difference to another problems and to another algorithms is the factors, the principal factors from a structure problem, from a structure algorithm structure. The function, the composite function depends on it. Depends on finding the principal and significant factors or features from problem structure and algorithm searching behavior. So, but the principal task is to generalize the.
No, I have understood the logic, the rationale behind the approach is quite clear. My only, let's say, objection was about the comparison, because there are some state-of-the-art heuristics also for the well-known one-dimensional beam packing problem. So my impression is that your approach should be validated by comparison with against state-of-the-art methods. But the rationale behind the method is quite clear. Now we should go to the next, to the last. Thank you again for your presentation. Thank you again for your nice, interesting presentation. We should go to the last presenter. I think it's here Rodrigo Sigueira, presenting the paper Multi-GPU Approach for Large-Scale Multiple Sequence Alignment.
Can you hear me?
Yes.
Okay, let me prepare my presentation here. I just have two screens here, so I have to fiddle a bit with it. Okay, let's see here. Okay. Okay, I'll share my screen here.
No.
No, yeah, not yet. I will do it. Okay. So, Chrome tab. Can you see my screen now?
Yes, okay.
Okay, so can I start?
Yes, of course.
Okay, so I'm Rodrigo. I am from Universidade Federal do Mato Grosso do Sul in Brazil. I will be presenting my master's degree work, which is multi-GPU approach for large-scale multiple sequence alignment. So this presentation will be divided into 5 parts, into 5 topics. Definitions, goals. I will be talking about how hybrid parallel computing works a bit, and I will explain the heuristics and what we did to improve it, and then our experiments, results, and final conclusions. So definition. The problem of multiple sequence alignment is a bioinformatics problem. And the idea behind it is that we try to this is just definitions. Okay.
Is on.
Is anyone saying something? Okay. So this problem, we try to do an analysis comparison between different biological sequences like DNA, RNA, or proteins in order to understand their biological functions, their structures, and to predict different proteins structures, and build also evolutionary trees, which are also called phylogenetic trees. So we try to understand which being originated from which other being, in the past, in order to construct an evolutionary tree. This is just some of the applications. There are many more, but as our time is quite short, I've picked this 3 here. So the goal of this problem is to, when you have multiple sequences, you will try to align the sequences by inserting spaces, so-called gaps, in between the characters of the sequences, or mismatches, so that when you're given a scoring function to transform a character into another, you will maximize or minimize, depending on the function, the total alignment score. So here I have, just for an illustration, a little bit of a small part of a sequence alignment of a protein of influenza. And usually this problem is solved by an heuristic called progressive alignment, which is divided into 3 steps. First, pairwise alignment, then a neighbor joining, which constructs a guiding tree, And finally, the progressive alignment which aligns sequence profiles in order to generate a final alignment between all sequences. We will get in more detail during the presentation. So the idea is here is to do it, to solve this problem as fast as possible. Currently, when you use sequential implementations of these heuristics, you have to wait quite a long time, sometimes weeks, depending on the computing configuration you have. So our idea was to implement this heuristic in a hybrid parallel computing architecture. What does it mean? We would use clusters of GPUs to try to do it and solve the problem as fast as possible by parallelizing our current heuristics. Also, we would try to do as much optimization to the current algorithms as possible. So the idea behind using a hybrid parallel computing is to take advantage of both fine and coarse-grained parallelism at the same time. So usually we split larger tasks into smaller problems, which are processed in shared memory environments and therefore parallelized in even smaller tasks. For this, we use MPI for coordinating our clusters, and CUDA, NVIDIA CUDA, for our GPUs to implement GPU programming. Starting to talk about the algorithm, the first step is pairwise alignment. And before going into pairwise alignment, we have to load the sequences into the memory of the nodes. And for that, we have to share and transfer a lot of data between different nodes in our cluster. And in order to make this burden a little bit smaller, we implemented a kind of data compression which can gain up to a third of, we can save up to a third of what a sequence would originally take of memory to store it. And this compression only takes 2 instructions to encode and decode, so it's quite fast. So for the pairwise alignment, of course, you can refer to the article, which we have more details on how it really works. But for implementing this step using a multi-GPU architecture, we distribute the pair of sequences we have to align into the different GPUs. And then each GPU aligns many pairs at the same time. In a GPU, we have something called blocks, which are like group of threads that work in a SIMD fashion, so single instruction, multiple data. So these threads, these cores, they're literally hardware cores. They process, they compute the same instruction with different data. So we use these to align multiple sequence pairs at the same time in order to save time, So while only one, when you do it sequentially, only one sequence pair can be aligned at a time. You can do it maybe thousands of sequence pairs aligned at the same time using this architecture. So the objective here of this step is to create a distance matrix between the sequences. So this matrix is calculated, divided in multiple GPUs at the same time, and then we join it, we gather all this data into all GPUs for the next step. In the next step, we use this distance matrix between the sequences to build a guide tree for our final multiple sequence alignment. This guide tree would be something similar to an evolutionary tree. So the idea behind it is to try to group different sequences which are closely related. So let's say if you have sequences for mammals and sequences for fish, you would try to group mammals together and group fish together so that these sequences are more closely related, and thus they keep together, they appear together in the final alignment, and then only later they are joined, they are aligned with the fish sequences. We do it, and this is important because when we introduce gaps or mismatches in these sequences, we cannot undo them later. So the idea is that if we can introduce as little gaps and mismatches as possible, our alignment in the end will be better. So here I explain a little bit how the algorithm works in this architecture. And it's important to note that this step, the second step, the neighbor joining or guide tree construction, have been implemented in a single GPU in the past. But as far as we've searched and as far as we know, this is the first work which implements this step using more than one GPU at the same time. So this part is a quite good contribution from our work. And of course, I would refer you to the article for further details on how it was implemented and how it works in detail, as we have only 4 more minutes. The final step, the idea is to traverse this guide tree and go aligning the sequences and produce pairs in order to gradually or iteratively constructing or building bigger and bigger sequence alignments. So we start with a pair, so 2 sequences that we align together to form a profile of 2 sequences, and then we align it with 2 more sequences at the same time, a little bit similar to how it was aligned in the first step, as I said. But here we have to use a different algorithm for reasons GPU memory is very limited, and we can only perform one alignment, one profile alignment in a GPU at a single time. So here we also have to take care of memory transfer or data transfer between nodes. And once again, in each GPU, an alignment is divided into smaller tasks in order to calculate it as fast as possible. I have only 3 more minutes.
Only 2 minutes.
Yeah, I'm just finishing. So the experiments we performed, we compared with Custom W MPI, which is a parallel implementation of Clusto. And Clusto is a family of solvers which is used a lot in literature. And also Clusto Omega. Clusto Omega does not use the same heuristics as we do, but currently they are the state of the art. So although they do not use the same algorithms as we do, we compared with it, so we can have a measure of time and quality of the alignments produced. So the data sets we use are here, and we use two different test environments in which these are only the relevant nodes that we used for our tests. So we have a table of results here. Once again, I have to refer you to the article for further details. We also use Belly Base in order to compare quality between our sequences and our competitors. Although we are a little bit worse in quality, we are not that far away. So our work is justified as we were focusing on speed. And here are the speed ups we got in the second step. And once again, as Costa Omega has a different algorithm as ours, their second step is a little bit faster. But in the general, when you sum all steps, we have a speed up compared to all experiments. And in conclusion, we implemented the first parallel multi-GPU solution, complete solution for the multiple sequence element problem. And we have presented significant speed ups in all heuristic steps. But there are some work in the future which can improve even more what we have presented in this work. Thank you very much. I'm a little bit late, but if you have any questions.
Thank you. Thank you, Rodrigo. Any question? Any question? There is a significant noise. I don't know why.
In my mic?
Okay. Apparently no questions. But can you hear me now, Rodrigo?
What did you say, sorry?
Okay, apparently we have no questions, but just a very, very short question because we have to conclude. But did you also address the issue of the power consumption in comparing your approach with other approaches?
Yeah, so our focus was only speed. So we wanted, only speed up. We wanted to do it as fast as possible. Then we performed a little bit of quality because there would be no purpose on being fast, but being bad. So our idea was speed.
Yes. But you have several future work points.
Yeah,
okay.
Sure.
Thank you very much again for your interesting and nice presentation. This was the last paper of the last session for today of the general track. So I would like to thank you all for your contribution, everyone for attending, and we will meet maybe at the conference tomorrow. Goodbye.
Thank you, Prof. Goodbye.
Thank you.
Bye.